Hello, everyone. Thank you so much for joining our community call. So the reason I wanted to have several topics covered in this call is because we have people coming from different backgrounds, and basically, we are joining different tech here. So we have people coming from Zig, which is a fairly new language for me and for most people who are coming from the Starknet side of things. And we obviously have, Starknet is new for people who are coming from the classical, maybe even just Web 2 development, not even Web 3. So I think it's important to cover, both, the Starknet stack, which is huge, actually has a lot of different components and is, quite complex. And at the same time, explain where, because we are really zooming in. We are zooming in on the Cairo VM, which is the heart of the stack. And it's important to kind of explain what it does, what it doesn't do. And because I've had some people from the community kind of slide into my DMs and ask things like, how does the VM generate the proof? How does it prove? And I'm like, wait a second, it doesn't prove anything. And so, it's important to kind of separate exactly what it's doing, kind of zoom out a little bit. And then we'll also do a little code walkthrough from Johann, and also like a dive into Zig a bit from Tama. So let's hop right in. So yeah, the presentation is the Cairo VM. Where does it sit within the Starknet stack? And first and foremost, why are we even implementing the Cairo VM? Yeah, so because we hear a lot that Cairo is a provable language, but if we zoom out even more, so what are we trying to prove and what actually makes Cairo provable? So first and foremost, it's important to understand that a provable statement is quite a simple idea in its essence. Yeah, it's when you have a mathematical statement of some equality or some property, such as, the number 42 is even, or this big number is prime. And how are we able to say that this is true or not? So here, because the property is simple, we can look at the last digit of this number and we know it's even. But here, it's not immediately obvious whether we can factor it or not. So we need to provide additional data, right? So we can add some witness, which could be the factors of this number. And this would actually be the proof as well, because whoever is checking it can be able to verify that this is true indeed. But in any case, we want to provide some auxiliary data in order to be able to convince the verifier that a certain statement is true. So what's going on? Let's go back to, so when we say Cairo, what do we actually mean? Yeah, because Cairo is a whole system of components. Yeah, but what is actually Cairo, the language without the virtual machine? So a Cairo developer, the one who is coding in the new version of Cairo, which is, we prefer not to say Cairo 1, but just Cairo. Yeah, so when we use the Rust-like language, Cairo, and we get the intermediate representation of it, Sierra, but we're not gonna get into that today. So what is important is we get a certain thing called CASM, Cairo assembly. So we don't even actually see it, so when Johann does the little code walkthrough, he's going to show you what files does our VM consume. But essentially, CASM is the Cairo assembly language, which tells you how to update registers of the virtual machine. And this Cairo assembly is crucial for for everything to be provable, because that is what is consumed by the actual CPU, which then has constraints enforced. Yeah, so what's important here is that, we have, it says Starknet here, but the point is that when we write code in Cairo, we are able to compile it to CASM. And at this point, we are not anywhere near blockchain, right? So Cairo can be written completely off-chain, it can be ran off-chain, and it can be proven off-chain, and it can be verified off-chain, right? So, and there are projects such as Giza that, operate fully off-chain, and this has nothing to do with blockchain. It just happens so that this provable property of Cairo is very well compatible with blockchain, so specifically with Ethereum, and so it serves scaling Ethereum. So Cairo without the VM is just you're able to compile it and you get this chasm. So Cairo, and this was not obvious to me from the beginning, is actually CPU air. Yeah, and then you're very surprised about it and you say, oh. What actually happens here? Oh my God, this let me move this stuff. When we implement the when we implement the CPU, it has its own air. So essentially, it enforces a set of constraints on everything that everything that we have in the trace and in the memory, right? So we check that we parse the instructions correctly, for example, that we extracted offsets, and that the memory that we have is indeed read-only and continuous, and all the registers are updated correctly, and so on. So I think here it's important to look at the white paper itself. The white paper is not maybe the easiest read in oh, I'm sharing the wrong window. Well, that's okay. So I can just show it here. So if you look at certain sections in the white paper, so particularly like page 33, when we implement the this algorithm in the virtual machine, we are actually implementing the CPU, which then generates the air with the constraints that we can translate to polynomials and to the polynomial constraints. And so everything that you can read in section 6, for example, in the Cairo white paper, it tells you about the rules. Yeah, so how do we get from the input state to the output state to the next state? And so this particular CPU, this process of going from step to step, is what the Cairo CPU implements. And later we want to see that we know such memory that actually trace and memory which satisfies these particular constraints and this error. What is also what you can, I mean, there's the white paper is like packed with complicated things, but what I find, for example, easily digestible relatively is, for example, the constraints for the memory, right? So we're trying to convince the verifier, yes. So when I say we, I mean actually the prover, yes. So when we are in the VM, we are just generating this memory and this trace, yeah. So one property of our CPU when we run the Cairo code inside it is that, for example, we have constraints on the memory that say that it's continuous and that it's read-only. So that read-only means that if you look at an address several times within the memory, you're going to see the same result. And then when you, there are no gaps. When you move from value to value, you either have the same address value or you increase by 1. Yeah, so in the ordered list. So if you haven't looked at the white paper yet, definitely look at it. It's a very interesting read. So let's get into slideshow again. Yeah, so Cairo is actually the language itself, right? So the Rust language from which you get to the chasm, then the chasm is, so here it says Cairo 0, but yeah, with Cairo 1, you get Cairo 1, Sierra, and then chasm, which then generates the trace. So of course, the trace, there's a lot of transformations before it goes to the prover, but this kind of alludes to the fact that we have 3 registers in the VM, and at each step we need to save the results of the state transition function. Yeah, so the trace and the memory, then they go to the prover. So the main question is, what are we actually proving? Yeah, the prover, not the VM. The VM did its job. It took the code, it produced the trace, the memory, and passed it on to the prover. So VM has nothing to do with proving. And what happens next? So we're trying to prove that there exists such a program, such a Cairo program with a given hash that we ran on this particular CPU with this layout. Layout is combinations of built-ins and memory that produced this particular memory and this particular trace that satisfy this CPU air and built-ins air constraints with the given inputs and outputs. So this is the actual statement that we're trying to prove, the prover is trying to prove, and then pass on to the verifier. So we're not going to get into the prover part here. But what is very important to note here is that it is general purpose. Yeah, so in Cairo, you can write, a lot of different code, and you don't have to generate polynomial constraints per each case. So one example is, for example, Noir, where you can, it's also a Rust-like language where you can write statements, but you have to generate, it generates a verifier in Solidity for you that you have to go and deploy on an EVM chain. So essentially, you cannot make use of shared proving, yeah, and essentially using the same infrastructure and the same maybe contracts or constraints for proving the same, proving different, not different errors, but different statements. Yeah, so here we actually generate very identical errors and not unique, you don't have to design any circuits, gadgets, and so on. So this is what it means when we say that it's general purpose language. Yeah, so Cairo. And I think we often mention built-ins in this case, and I think it's very important to just mention that built-ins are additional chunks of code which are kind of done outside of the CPU, but we just reserve some memory for it. And a very easy example is a bitwise built-in, because it just uses 3 cells where you say, okay, I have one cell A, cell B, and does cell C actually equal an OR, XOR, or an AND of these 2 cells? So you kind of have memory which is assigned inside the memory to this built-in. And so yeah, so some of us are working on built-ins. I'm working on the elliptic curve operations built-in at the moment. So there are actually other built-ins that we still need to merge. So there's there's work to do in this regard. I think, yeah, I think this is the end. Did I mention anything? Okay, I'm good on time. So yeah, I hope this maybe made a little bit of clarity, yeah, that the VM doesn't prove anything, and wait, sorry. Yeah, that the VM is yeah, generating the input for the prover. I will stop here because we have 2 more talks, and then we will accept some questions from the community. So, Johann, are you able to share screen?
Yeah, sure. Let me see. Unless you
Security, did I?
Disable it for me because you're prejudiced, but
No, wait, share screen. Now I need to turn that on.
I had to grant access, so I'm gonna have to restart 1 second.
Okay. Yeah, guys, if you have questions, maybe with regard to this topic or maybe a bit more generic Starknet, just throw them in the group chat. Um, did not do
Maybe I have like a stupid question, but like the change from Cairo 0 to Cairo 1 is quite drastic with a lot of change and a lot of stuff. It's not like a simple update, but something really different.
Mhm.
Why this choice now? Because it introduced a lot of complexity. I have heard that this is to mimic a lot of properties of Rust and to be more developer friendly. Do you know more about this choice? Because I think that this move a lot of stuff in the Starknet ecosystem, breaks a lot of like of compatibility stuff and lots of new work, compatibility issues and stuff like that. Do you know more about this choice now?
Um, I joined the company when actually Cairo 1 was in was already there, and
Okay.
it became kind of the go-to language. But essentially, yeah, it had with like a very steep learning curve, and the introduction of the Rust-like Cairo version, it just made it's still difficult. I mean, Rust is a difficult language as well, but
Yeah.
it made it really expanded the developers that started jumping into Cairo. So it's mainly with oh, and there's some helpful links in the chat. No loops. Oh, okay. So Akash wrote some Cairo 0 and
Yeah, it's also
Yeah.
with Cairo 0.
Another
you can
point?
include failed executions.
Fine. Would
Part of the
really
reason
thanks.
why they included the intermediate layer that Cairo 1 compiles down to is so you can prove that executions failed in the sequencer.
Fine. Great. Thanks.
Timothée, you were saying something too?
Yeah, but I was about to say exactly the same thing as Johann, is that Cairo 0, you could write Cairo 0 programs that are not provable, especially if they fail during their execution, while Cairo 1 program, as long as they are compiled, they are provable because the failure is provable. And this was really important for Starknet, actually, because it allows us to charge user for failed execution. And if we are not able to do this, we are opening ourselves to a DOS attack, where we will be executing a ton of failed transaction and stealing the chain without getting any money out of it. So that was the main reason for having something new, was to introduce the intermediate layer, which is Sierra. So now Cairo 1 compiles to Sierra, and only things that are provable can be compiled to Sierra. And then there is a second step, which is Sierra to Chasm. And Chasm can file in a non-provable way, but Chasm coming from Sierra is always provable. While Cairo 0, it was directly from like this hard to write language to Chasm without the intermediate step.
Fine. Thanks for the detailed answer. Yeah. Understood. Thank you.
Okay. Is my screen visible?
Yes.
So I set a couple of breakpoints through the code base. And
Johann, sorry, we have a comment that you are not very well audible.
all right. I'm gonna turn
Speak
on
up.
my microphone. Is this better? No, not better.
No, not really, but I can manage. Maybe because I'm not using a headset. But
Yeah, I can hear you too.
Okay, let me adjust my microphone settings. This better? Yeah, higher?
Yes.
Okay.
Yeah, it's great now.
Okay. All right, so we're going to start Ziggy STARKDust. Gonna run it. This is the config of it. So we're running the Fibonacci program and we're using a plain layout. So the basic high level thing that I wanted to touch on is when we put in the Fibonacci program, we're essentially taking a bunch of instructions and we're loading it into memory. Then we're stepping through for a program counter into an entry point, taking the instruction and taking the encoded version and decoding it. Continue, and then we eventually take the instruction, compute operands, and get an operands result. That is expected, that's how most CPUs work. But the thing that is also happening alongside just the typical fetching and evaluating instruction is this generating of a trace. And what we're doing is per each step, we are tracking the program counter, the allocation pointer, and the function pointer. And we're doing that for each step, and we're also tracking for every step the changes in memory. If you want to get into the actual instructions and the state transition rules, I think there's a couple of good resources. One is the sections 4.4 and 4.5 of the white paper, and then also the legend, he encoded the decoding and execution of a Cairo program in a Google Sheet. So if you want to check that out, it's a good way to get a feel for the instructions. But for the sake of today, the thing I wanted to emphasize was just like that broad general flow of taking instructions, decoding, and executing, and then getting into the details of after. Just gonna skip. Continue. And this is basically the last time we're going to run this. Then so we want to get to we eventually, when we get to the Cairo runner, we get to this point right here, where we basically take the traces that we're generating and we have to relocate them. And this gets into the interplay between, this VM is essentially generating 3 artifacts that we're going to hand to the prover. And the first artifact are the traces of the registry traces and then the memory. When we are executing the program, we are putting it in terms of making it kind of like having it conveniently as possible to allocate memory. So this is where we have segments. But then when we want to pass it to the prover, we have to put it in terms of making it as efficient as possible to establish constraints on it. So this is where like the whole relocation process comes in, where we basically take that extra dimension of a segment and we make sure that the memory is continuous. And the relationship of thinking about it in terms from the VM perspective and then thinking about it into the prover's perspective plays into built-ins as well, right? Because like the value proposition of a built-in is essentially to try to get the same computational result with less amount of steps. So the VM, we have steps, but then when we are taking the end of the day trace and handing it to the prover, there's also the dimension of how many memory cells that we have to consider, right? And this is where we have this notion of a layout. A program has a layout, and the layout essentially establishes there is the constraints of the CPU, then every single built-in has its own constraints and has its own memory cells, memory cells that also need to be considered. So like there's this trade-off in how the Cairo VM was designed in trying to make as efficient computational steps as possible, but also minimizing the amount of memory traces, memory cells that are necessary in generating and improving traces. And it's a really interesting and distinct thing that kind of, if you look at other ZK VMs, they weren't necessarily designed for trying to make that balance of trade-off between memory cells and computational step power. And I think it's really interesting to think about the design space from that perspective. But yeah, that's about it. I cede the floor. Relocate memory is pending because someone just needs to, we have the logic of writing it, and we have the logic of relocating also. It's just a matter of hooking it into the runner. If you feel excited to do so.
Isn't someone working on that? Oh, okay.
Yeah, I am working on it, and hence I had queries regarding.
Oh, okay. Yeah, if you're having any issues, just ping us in Telegram.
And we
Yeah,
have also
sure.
like the PR about like moving like the relocate memory from segment to memory with additional unit tests that is pending, I think also. And maybe we'll need this one to continue.
Yeah, sure.
Okay, I got the hint.
Yeah.
Okay, I have a question.
Shoot.
So I've seen instances where the built-in is compared to precompiles in the EVM in Solidity.
Mhm.
I like thinking about it like that, but then I really don't understand how okay, so basically, if we look at is a built-in like a precompile? And if that's true, how does that work in this case?
Well, I think the resources, it's a little bit more complex with the built-in. For an EVM precompile, it's essentially saying you're saving gas, and you're calling directly to lower level code. But since the interplay of like what makes, because like there's a couple different dimensions going on. Like one is like the execution of the VM generating the trace. The other is the execution of the prover in generating the proof, right? So a built-in can, relative to like a precompile, when you add it to the EVM, it doesn't really affect, correct me if I'm wrong, it doesn't really affect other programs when you add it as available. But when you use a particular layout that makes available a particular built-in, every other program, if it doesn't use your built-in, will implicitly pay a cost, because even though if you would use it, it would require less steps computationally, it will always demand more memory cells, which also impacts the prover costs. Does that make sense?
Just to clarify, did you say whether I use a built-in or not, you still kind of bear the cost when you're running a program?
Depending on if you're using the layout. And this is what makes layouts kind of complicated.
Okay, can you explain layouts a bit?
So basically, if you see a built-in as its own small type of CPU, a layout, and then basically a layout sees like you have the big CPU that requires a certain allocation of memory cells. And then for every other mini CPU, you also require an allocation of memory cells. And it's not free in terms of it creates prover complexity from the prover's point of view.
I think the example we had earlier would actually illustrates this very well, because literally when you have a bitwise, I think the bitwise built-in is like the easiest to understand, because it literally has two values and it needs like 3 memory cells. So what you need to do, first of all, you need to allocate these 3 memory cells per built-in, because if you were calculating all the like the built-in inside your Cairo code, you would essentially use a lot more memory cells, and the prover would have to prove that whole like memory, right? And here, the prover only has to prove that these 3 cells, their relationship between each other is what you expect as per, you know, the built-in that we're talking about. So it has its own polynomial constraint, its own error, which just says, hey, connect these 2 cells and tell me that they are the bitwise AND of each other. So you have a much simpler polynomial in there. And then using it or not is up to you. So you can use the VM with a plain layout, which like doesn't have any built-ins, or you can actually like have all the built-ins there, even if your program doesn't utilize them, and you can save on certain memory cells. I might not be 100% correct there though.
Okay, I think that makes sense. I will just do some extra reading to clarify. Thank you.
And I think also that is why if you look at the different implementation of the VM, either in Python or in Rust, you have really a lot of different layouts, almost one for each purpose. Like you have maybe more than 10 layouts available in each of the VM.
Nice. So we have, okay, cool. Yeah, we have 22 minutes left. So, Tama, would you like to jump to the
Yeah, for sure.
big intro, the most interesting part of our convo?
Let me share my screen. Can you see my screen right now?
Yes.
Perfect. So the objective of my presentation there is to present a little bit more about Zig and it's the interest that we have in Zig to implement a VM, and more particularly a ZK VM. Why Zig and not Rust or Go or C++ or any other language? So what I will do is I will present briefly the main feature that can distinguish Zig from other low-level language like Rust, C++, or Go. And I will dive then into some example into our code base to present some very basic feature of Zig and why we are using this in our context. So the first thing that we can see from Zig is that there is no hidden control flow. What does it mean? It means that the code that you are writing in Zig always do what you want to do and what is written. First, you have no operator overloading. In Rust, this is a little bit different. For example, if we take the precise example of Rust, because some basic operator like the plus here can be overloaded by some traits. For a very basic example there in Rust, if you have like a structure that is a point structure with X and Y coordinates, then you can implement the add trait from the standard library out there. And so you have a function add that can do what you want, any operation you want. In this case, it will add like the X and Y coordinates. And so when you are writing the plus between two instances of the point structure, it will in the background call the add function. This is what I mean by overloading operator, and this is not the case in Zig. You have not this. When you write a plus, it only writes a plus, and if you want to call any other function with any other particular feature, you need to write it explicitly. There is also no possibility to jump away from a call, like there in C++, in Rust, sorry. You can have like a panic, and in this panic, if I execute my main function out there, you have some basic operation A, B, C, D, and then you call the foo function. But if you panic inside the foo function, then it will prevent your code to execute the bar function. And so, for example, this print statement will never be executed because the foo function panicked before. And this is not the case in Zig. For example, if you call that in Zig, it will always call the foo function first and the bar function first. Even if there is an error, it will be handled properly. So what does it mean? It means that you have to be really careful, because there is more like there is more controls that you can have over your code, but then you need to be really careful and to know exactly what you want to code and what you want to achieve. Also, one important point is that you have no hidden allocation. This is some quotation from the Zig official documentation. And so the Zig language never perform any memory allocation or management on behalf of the programmer. This is why Zig has no runtime, and why Zig works really seamlessly in so many different environments, because the programmer has to handle like the memory management on his own with different allocator, and you can design your own allocator for any purpose that you want. So let us dive into a brief example there. You can import the std library, standard library, that is an optional library inside the core repo of Ziglang. And then you can, from the memory module, you can export the allocator type. And then into these very basic tests, you can assign a buffer allocator into the heap and init your buffer with a given size. That is the purpose of this fixed buffer allocator. And then you can use this allocation of memory to concatenate two strings out there, foo and bar. So as you can see out there, you need to allocate your own memory, and there is nothing hidden. So there are different type of allocators that are available to you. You can design your own, and there is also like a testing allocator that you can use for all of your unit tests to freely test the behavior of your function using allocator. And then if you call inside like the what is inside the concatenate function is like it first allocates some memory, because as you can see out there, you pass your allocator as the first argument of this function. So you need to design the allocator, and you can even pass it as an argument of your function, and you can play with it. So this means that you have also to take care of your memory to know what you are going to do. And the advantage of that is that you can really build customized stuff, but you also need to always take care about what you are doing. There is also something that is really interesting to Zig, is its package manager and all big system, all like the build system. I will like distribute the link of this after the presentation, but here you have a very interesting link out there that describe you in a very complete manner, with a complete tutorial how you can compile a C or C++ program. And we have also like a project on this with Abdel about like the stone prover that is currently written in C++, but you can compile it instead of using classical CMake. You can compile it with zig.build, a build.zig, file. So you can use Zig to build any C or C++ program, so that you can interact with a code that is written already in C or C++. What is really important and what we want here to emphasize is the learning curve that is drastically reduced compared to other equivalent language like Rust. You probably know that the learning curve of Rust is really steep, and you have to learn a lot of concepts, the formulation of the function, of the traits, of everything is really complicated. But in Zig, everything is really straightforward, because it always goes into the minimal, and minimal stuff less verbose implementation, and really always the minimum that you need. Also, you can see that if you have collaborate already in the project, but the project is quite big, and it compiled really fast, because, for example, when you execute the test, you can see that it takes only a few seconds, but it compiles the whole project and it executes all of the tests. So what does it mean? It means that, and if you do exactly the same thing with Rust, you will see that it is much more complicated, because Rust introduced some additional complexity there and check measure for safety, but this lead to very long compile time. But due to its minimal implementation and lower count of high-level expression and less safety assurance that must be handled by the programmer, Zig processor can compile really fast and faster than Rust. You have also like a stdlib that is really well written, always updated by the community day by day, because it is in the main repo. And what is really interesting for us are two stuff. The first one is that you have a big int library. You can go into there. And so this is native in Zig, and you have all the operations that you need within big int to handle properly begin doing multiplication, basic operations, subtraction, multiplication, and all the classical operations that are handled by different type of libraries in Rust. And you have also a native crypto and hash util library within std natively that is also really useful, and we are using this inside the VM to avoid implementing again the Ketchak or any other gadgets that we need that are already implemented within the stdlib. The performance, of course, this is why we are all there, are really interesting. You have some benchmarks that shows you that the performance are similar or most of the time better than Rust, C++, or even C sometimes. Now that I have presented the main concept of Zig, let us dive into like some example of the code inside our own code base, because what is of interest for us is the implementation of our Cairo VM. So the first very interesting feature is like the default fields. I will present one example out there with our instant definition that is used in the context of ECDSA instance definition for a definitive usage inside the buildings. As you can see there, we define a simple structure that is ECDSA instance def, and we define different fields for this structure with different types, and we position there default fields. These default fields are known at compile time, and you can initialize an instance of this structure very easily using this default function. So what does it look in reality? It is there. So you see, by writing only this statement, you init an instance of this structure, and by default, this instance will be constituted of this initialization by default, no at compile time. On the other hand, if you want to do that inside Rust, you need to define a default function and put your field there and call the function to init. So this is, for example, a basic advantage of Ziglang there. You have also like the inline for loops that are for loops that can be inline, and in this case the loop is unrolled, and it allows to do some code step in an unrolled manner, but just putting the inline words in front of your loop operation. I will show you a basic example there also, like here. You need to know, for that, you need to know at compile time the bounds of your for loops, but we are using that, for example, to create a field element from a byte array inside our field structure. And so as you can see out there, we are doing a loop for 0 to 4, and we are putting the inline word in front of the 4. This means that in reality, at compile time, this loop is unrolled. And so this is the same as writing this statement 4 times. That is another example. You can also very easily play with types in different situations. For example, we will take the example of the initialization of like the basic Cairo VM structure that is our core structure. And out there, you just define a self that is defined at the beginning of the structure there, and it represents the type of the structure. And when you write this, the function at compile time knows that you want to return a self element. And so in the return type, as you can see there, you don't have to write again the type of the structure that you want to return. You can just put a point in front of your global structure, and the language knows that you are going to return a type self. And if you miss some field, for example, it will throw you an error because it knows that it returns self. As a comparison, in Rust, you have to write again the name of the structure to define it, even if Rust knows that you want to return that. In switch operation, also, this is very interesting to look at, because you are doing basically the same thing. You want to, for example, here we have a self that is of type self. And if you switch around this self, you don't need here to recall the name of your enum that comprise the different elements. You can just put dots and the name of the element where you want to switch. So the different branches of the switch, and you don't need to recall the name of the enum where are located these elements. This is really practical because less verbose implementation and a lot of stuff are simple to read and to implement. And the compiler will throw you an error, obviously, if there is something wrong there. As a comparison, in Rust, as you probably know, for doing something really similar, like a match, you need to recall the name of the enum each time. So you have like a more verbose implementation rather than in Zig for this same basic example. Then we have also like optional types that are really nice to read and to handle. Why? Because this is just like they are just symbolized by a question mark. The question mark symbolizes the optional type. And so this means that here, for example, you have a integer, and here you have an optional integer, meaning that this integer can be either an integer or a null value. This is equivalent to the option type that you have in Rust, for example, but you can play with it really easily. You don't have, for example, to put this option word. You have just to put the question mark, and you don't need to put the sum also, because this is directly understood by the compiler. When you put like the integer value, it knows that this is the equivalent of sum there. And you can also play with it in a very basic example using the if, and we are using this not here, for example. So you can use the if statement there to know if this A element is null or like having a value. And here you can put that by reference to use it directly as a value there. So the if statement can be used as the equivalent of unwrap in Zig, in Rust, very easily. Also, like one thing that is very important for us is that the U256 unsigned integer In Rust, there is no support for that. So when you need to design something for a big integer, you need to go through a big int library. And this can be really complex and with different imports and stuff like that. But in our case, we can just go into U256 to manipulate some stuff around our fields. And for example, I will show you an example out there in the code base in one of our tests. You can use directly, you can construct a felt 252 from an integer, and this integer can be a U256 directly without any manipulation with a big int library. And so you can use that to handle very huge number without having to dive into like some kind of complex library. You have also 3 remaining steps that I wanted to present, like the block manipulation. In a block, it can restrict the scope of something into a block using this very small keyword block, and then you can end your block with a break statement. And so this is a very compact format to limit the scope of some function or some block and to return something at the end of your block. The for loop also are really easy to manipulate. This is really straightforward. You don't need to learn anything, basically. You just need to iterate over something. As you can see there, you can just write the for and the array that you want to iterate through. And if you want to iterate through some index, you can just put 0 to something, and it will iterate through the end of the array automatically. And then you have this keyword to indicate in the same order, respectively, where you want to iterate. And so there is nothing to learn, basically, and this is really easy to handle even from a beginner programmer. And finally, the standard libraries that I find very interesting because there are a lot of support, a lot of stuff. And even if it seems quite small compared to the Rust code base that is really huge, but with a lot of support from the Rust community, in the std library, you have basically everything you need. The vector are replaced by array list. This is the equivalent. A vector in Rust is an array list in Zig. And the hash map, you can find it both in Zig and Rust. And there is a lot of support. And in our code base, we are using a lot of feature of the std-lib. For example, in the memory there, you can see that we are using a lot of array list, also some hash map very frequently. And they are really easy to manipulate. The name of the function are really simple. And so you can find almost what you need inside this library. This is all I wanted to present to you today. So if you have any question or stuff like that.
Amazing. Thank you so much. That was such a good overview of Ziglang. Super cool. Yeah, if anyone, well, no, I guess here everyone has already touched Zig. By the way, if our call cuts off at 1 hour and 1 minute, thank you everyone for coming. But if not, we actually, okay, so yeah, so this is what scope of Zig with Starknet ecosystem. So we have a fantastic news. So our brave developers, Johann and Tomat, so they are applying for a grant for a developer partnership with the foundation. So I'm sure that everything is going to go well, and they're going to define the scope soon. But essentially, the goal is to implement the sequencer and the prover. So I believe that there's a very big future for Zig and the Starknet ecosystem because of how much easier it is to code. And it is, I don't know, I absolutely love Zig. And there will definitely be opportunities for open source contributions and possibly even more full-time relationships, but that will all be announced by the guys later. Yeah, so we're all very excited and really looking forward to how Zig will perform in the blockchain world, and not just in Starknet, but in other places as well. And yeah. Okay, so it's time. Everyone, I believe, is in our Telegram chat. So if you have questions, ask. We're going to review the pending PRs in the next 3 days. And yeah, hopefully the MVP with the hints will also come within the 1 week, let's say. So we have, what are you laughing at? We're working on it. Okay, thank you very much, guys, and see you soon. Bye-bye.